On implication. Implication is a logical connective. A logical connective like if and only if, or, and, XOR, that sort of thing. A logical connective will take two statements, and depending on the order, or sometimes not depending on the order, it will give an output of another statement. So if I have statement 1 and statement 2, and I put between them a logical connective, say and, then this becomes a composite statement by nature of the logical connective, in this case and. Implication in particular is read if X, then Y. Okay, so if X, then Y. You can also use this arrow. And order is important. The implication of X onto Y is not the implication of Y onto X. Okay, so in what cases are the implication true? Let's take S1 onto S2. S1 implies S2. Or if S1, then S2. If S1 is true and S2 is true, then the composite statement is true. If S1 is true and S2 is false, then the composite statement is false. And then in both cases that S1 is true, that S1 is false, the composite statement, the implication itself, is true. And this is somewhat counterintuitive that you could have a false hypothesis, and from a false hypothesis you could disregard the truthfulness of a conclusion. But it actually becomes very useful. So let's give an example. So a true example would be if X is equal to 2, this implies X squared equals 4. So if this is true, then this is true. If we were to say X is equal to 3, then this is false. Our hypothesis is false. Our first statement is false. And this would be false. But if we look at our table, false, false is true. So the implication holds, despite the fact that in some particular case, the hypothesis is false. As long as when the hypothesis is true, the conclusion is true, the implication is valid. So let's do a false example. Let's flip it around. Let's say if X squared equals 4, that implies X equals 2. Okay, so the issue we're going to have here is if X were to equal negative 2, then X squared would equal 4, which means our hypothesis is true, but our conclusion would be false, seeing as how we decided X was equal to negative 2. So this would be a false implication. This statement is false. A real-world example you might have heard is, if pigs had wings, then they could fly. That's a true implication, because pigs do not have wings, and they cannot fly. So the implication is still true. Here's another one. Assume that if John had left at 5 a.m., he would be here by now. If we know he's not here, and that if he had left at 5 a.m., he would be here by now, then we can show that he didn't leave at 5 a.m. Because if you assume he did leave at 5 a.m., then he would be here, but he's not. So the assumption leads to a contradiction, which means its negation must be true, which is that he didn't leave. That's verbally how I would explain that. Let's get into some vocabulary. So if I have a statement, X implies Y, then the converse to this is Y implies X. If I have a statement, X implies Y, then the inverse would be not X implies not Y. So this is converse. This example is the inverse. And the last one is the contrapositive. So if we have x implies y, the contrapositive is not y, implies not x. Just because our initial implication is true doesn't necessarily mean that our converse and our inverse are true, but it does imply, in fact, it's logically equivalent to our contrapositive. So to demonstrate this, okay, in my notes I just do the table thing, so I don't have a good example for that. And then contrapositive would be logically equivalent to the implication itself. So x implies y. Again, this is logically equivalent to not y implies not x. In the case that y is false, the only case where this isn't true is the same where this isn't true. Here, when y is false, in all the true universes, the only one where y is false, x is also false. And then we can't determine anything about x. Let's talk about using implications in proofs. We can have a false hypothesis in a true proposition. So if I say, if 2 plus 2 equals 5, that implies that 4 equals 10 minus 4. The implication or the hypothesis is false. But we can prove that the implication is true. We can have a good proof around this implication. So if I multiply both sides by 2, we'll get 4 plus 4 equals 10. And then I can subtract 4 from both sides to get 4 equals 10 minus 4. And this would be a correct proof for showing this implication is true, even though the conclusion is false and the hypothesis is false. You can also have a correct proposition that's proven in a ill-formed or bad way. So if I have, say, 2x equals 4 implies x equals 2, this implication and this proposition is true. But I'm going to show a proof that would be incorrect to use. So if I say, well, okay, say x equals 2, then that means that 2 times 2 does in fact equal 4, so this implication is correct. This would be irresponsible because we're assuming the conclusion instead of assuming the hypothesis. We can also use the vacuous nature of a implication in a proof to save us work. So a vacuous hypothesis is one where either false implies true or false implies false. It's vacuous because both of these implications are true, and since they're both true, if we know the hypothesis is false, then we can't actually derive any information about the conclusion, knowing the falsity of the hypothesis. So say that x is an integer, a positive integer, and I don't remember the set for that, so we'll just say that that's z. I don't really remember if that's a set of positive integers. Say that x is a positive integer. We can say this implies n times n plus 1 is even. I don't remember what set that is, so it's just going to be in the set of e. We know x is either even or odd because it's a positive integer. Let's assume that x is even. If x is even, then, you know what, I should say n. If n is an integer, that implies n times n plus 1 is an even number. If our integer n is even, n times n plus 1 is even, because n is even, and n times any integer is even. Okay, if n is odd, then we have n times n plus 1 implies it's even, because for an odd number, when you add 1 to an odd number, it becomes an even number, and any even number times any other number is even. Now, in any particular case, one of these hypotheses will be vacuous but true. So if n is even, then the odd implication will be vacuous but true, because false, true is true. In the other case, that n is odd, the even implication, the implication we use for the case of even numbers, is vacuous but true. For the same reason, false implies true is true, which shows you that you can leave vacuous implications in your proof as long as the hypothesis is false. It's okay for hypotheses to be false in your proof. And that's kind of why they're useful in the first place. So that was, you could get rid of an implication by just in any like, let's say we have a big number, say 100 plus 10 to the power of 8 plus 7 plus 2, something really that would take a lot of time to work out. You could work it out, say it's even or odd, and to get rid of the corresponding implication to like save statements or to remove vacuous statements. But this is much more work than just leaving it in and saying, okay, I know this is going to be an integer, so it's okay. So I'm just going to leave these in so I can just jump straight to the conclusion that this is even. This is only even if this is equal to n, meaning this isn't always even, but if we know that this expression here is equal to n, then we can know for sure that n plus times n plus 1 is even. And then let's talk about proof by contradiction. Proof by contradiction is also called reductio absurdum, and it basically works by assuming that something is true and then showing that it leads to a contradiction. If something that is assumed to be true leads to a contradiction, then it must be false. And vice versa, if something that is assumed to be false leads to a contradiction, then it must be true. So like in the case true, false, this is the only case where an implication is false. So like let's say x is a positive number, and also that sine of x equals 1. We want to prove that x is greater than or equal to pi over 2. Okay, so to prove that x is greater than or equal to pi over 2, let's assume that x is less than pi over 2, which is the negation of this statement. If x is less than pi over 2, then consider the fact that we also know pi is greater than 0. Well, if x is less than pi over 2, and x is greater than 0, we know that sine of x is greater than 0 and less than 1. Because in the case x is equal to pi over 2, then sine of x is equal to 1. In the case that x is equal to 0, then sine of x is equal to 0 as well, which can't be true. So we know that since sine of x is greater than 0, it can't be equal to 0. And in the same sense, we know that sine of x is less than 1, which means it can't be equal to 1, which means that one of our statements is false, which means our assumption led to a contradiction, which means that our assumption is false, and the negation of our assumption is the thing we were trying to prove, which is true, and that is proof by contradiction or reductio ad absurdum.